Okay, today we're going to finish up on our binary trees, or actually on binary search trees. We will come back to another binary tree, so keep in mind that a binary tree is simply a data structure where every node has its data value and two children, and the binary tree has to be set up in an order like this where all the arrows flow down, there's no arrows going up. And then, so that's what a binary tree is, but a binary search tree is going to add another requirement such that for every node, everything to, let's see, to the left is smaller and to the right is greater. They wrote it backwards on the screen. Larger data is to its left and smaller data, larger than it is its left child, even though that's not what they drew. Huh. Oh well. Am I reading that right? Don't the English not match? Okay, well anyways, ignore this. English does not match the picture. The data less than 60 is all to the left, data greater than 60 is all to the right. And what was the advantage of this?
Searching is easier.
Searching, well, maybe not easier, but faster. Faster. Okay, so they have, speaking. Have a definition, is empty, or it has a root node and has two sets of nodes, left subtree and right subtree, so it's recursive definition because it's defining itself with itself. And key in the root node is larger than every key in the left subtree and smaller than everything in the right subtree. Okay, that makes more sense. And then, of course, all the subtrees have to be binary trees. It was where it gets its recursive. Therefore, the definition recursive. All right. That's nice. Do we get a picture? All right, so searching, the nice thing about searching, which they didn't show a picture, but we talked about last time, is that when you're searching for a number, good morning, you compare it against the root, and if it is root, you return. If it's less than, you can go less than the root, you go down the left tree. If it's greater than, you go down the right. Therefore, you can cut in half each time, or hopefully cut in half each time, every time you visit a node. And this resolves to, in average or best case, you have log n. But we did talk about last time that if you added nodes in a certain order, the binary tree or binary search tree essentially becomes a linked list. And then searching would be O of n. We will talk about how to fix that on Monday. But right now, just keep in mind that there is a worst case scenario where it can become a linked list, but on average and best it's log of n, which is what we just assumed. Okay, inserting. We did talk about inserting an item, and here we actually wrote the code last time, which was add, which was to go down the binary tree and figure out where this node needs to be placed, and then once you find the empty spot, you just stick there. Now, on to the first thing we're going to talk about, because today we're going to finish up with talking about delete, and then we're going to talk about function pointers, which are a very powerful tool inside of C. And of course, since C++ is an extension to C in a way, C++ has it as well. But right now, let's go ahead and talk about delete. So here's our tree. Actually, let's go and do this on the board because this gets really complicated. Well, not really complicated. This can be complicated. All right. How's this marker? How's this marker? Oh, much better. All right. Start giving me numbers.
5, 2, 7, 20, 4, 9,
Yeah, anyone else can just chime in at any moment, guys.
12,
All right. 6, great, thank you.
1,
1, all right.
Y'all know I'm not the only one in this class.
-3.
-3. All right. Our random number generator is really slow this morning. 10? 47. Let's see. We'll go with 3, and then well, we can't put anything here.
What about 5? Where would 5 go?
5's up here.
Oh,
But
easy
it's
enough. Just kidding.
Put an 8. No, that's okay. Put a 15 right here. We'll put a 30, followed by a 56. Okay. Let's see if I can come up with some good test cases or what's going to happen. All right, so we want to delete a node. There are actually 4 situations where this happens. And okay, let's go do that. So we have plenty of room. Perfect. Have a big head in the way? Sure. So 1
Can't hardly see that.
node. Why can't you see it? Oh.
It's just
So it's too high is what you meant to tell me. Too hot. Now my big head will be in the way. Node is a leaf. Node has left tree. Node has right tree. Or I should say node. And 4, node has both. Okay. So, if we want to delete 56, how would that happen?
you just get rid of it. You set the 47 equal to point to null.
Yeah, you just get rid of this, and then it points to null. All right, doing great. Let me put the 56 back in there. So, what would we do to delete the 4?
Set 2 to point to 3.
So, what, sorry?
Set 2 to point to 3.
Okay, so you basically take this away, move the 3 up here, and then the 4 is gone. So to remove the 6, what do we do?
Get rid of it. Set to null.
Yeah. No. All right. Now let's make this tricky. I want to get rid of the 7.
Now points to 20. Delete 7.
So 5 points to
I'm thinking this in a linked list.
5 points to 20. Let's see. Can we do that? I think so. Yeah, you can just move that 20 up there, and then you're still good, right?
I think so.
Still good? Why are we not good?
That's the 8 and the 9.
But no, they're between 5 and 20, so that's good.
Okay.
Yeah, it's good. The real problem is now what happens when we want to delete 20?
You lose one side. Look at the bottom.
What are we losing? Oh, so we just need to erase all of this? Is that what you're saying?
No, we would lose it if we picked
Okay.
1. We would lose the other side.
Right, you can't just pick 9
and
or 47. This is the hard one. So what's nice is when it's a leaf, you get rid of it. If it only has a left subtree, then you point to the left. If it only has a right, you just point to the right. But if it has both, which is what's happening over here with the 20, what do we need to do?
Give up. Point to both.
Point to them both. Well, because 20 has 2 children, and each of them have a good number of nodes. So what do we do if we want to delete 20? What number could replace 20?
as well specifically? 15 probably. but-
15 could. So, so what Blake did was take the greatest of the left tree, go to the left, take the greatest, which was this 15. Does that work? Is it a binary search tree? Yeah, it's a binary search tree. So, if they have both, then you need to find either the greatest of the left side or the least of the greater side. Now, what has made this even harder to do actually, let's do this. No, let's do this. I like it. All right, now what do we do?
You pick the right side.
You picked. Well, I mean, the right side could have the same problem.
In this particular example, you grab the 31, but I feel like that's not the point.
You can't grab the 31 because 30 is less than 31, but then would be on the right side.
Oh.
So 30, again, your only two candidates that you can choose are the 15 and the 30. But we've actually already solved this problem. I just did so quickly that you missed that.
Move everything up a level and then move the lowest of the left, or the highest of the left and
So
the
hold-
lowest of the right.
So we were over here with the 4 and the 3. What do we do when we want to delete the 4? We just shifted this up. I mean, we could have this, right? Now I'm going into kind of cheating by going to numbers, or the decimals, or fractions, or whatever you want to call them. But if you want to delete the 4 and there's nothing to the right, you just shift this up. So if you want to delete the 15, you just shift this up, right? So there's actually not a problem here as long as you do this. Binary search tree. All right, that's delete. Everyone got this?
Yeah.
Oh, shouldn't point. Do I do this instead? This, or do you want the thumb? I'm asking. Is it too early? I'm sorry. All right. Ooh, team looks attached after I've already been inside of attached. All right. So delete, let's watch it pictorially. Hey, look, it's the same thing I wrote up on the board. The node to be deleted is a leaf. Delete has no left subtree, has no right subtree, and a non-empty left and subtrees. All right. So they are going to delete 45. They don't show you the picture because I don't know why, but there's a 48 and a 45, so there's a 45 here, so they just deleted that 45 and it's gone. On this side, they're deleting the 30, which was located here. So all they did is shift everything from the right subtree up because it doesn't have a left subtree. And that's why the 50 points straight to 35. They want to delete 80. Notice 80 was over here with nothing on the right, but stuff on the left. So they just took out 75 and 77 and just shifted it straight up. And over here, they're going to delete the 50. Where's the 50? 50 was right here. Which one did they go with? They went with 48. So in order to fix that, they first had to make 40 point to 45, right there. And then they took that 48 and put it all the way up to 50. How we doing? Great. All right, so let's go code this up, or at least part of it. Class code. Actually, we should take our last one, right? That way we don't have to re-implement things. Yeah. So quick review, we got our binary search tree node, mval left and right, and we could get the values and set them. And excuse me, so our binary search tree, we have a root constructor, we implemented add, is that right? And print, we didn't do contains, but today we'll start on remove. And do we have remove already stubbed out? Oh, we do. Great. So, if we want to remove a node, what's the first thing we need to do?
Find what we want to remove.
Right, so how do we find something in a binary search tree?
Binary search.
Sure. Oh. Go ahead. You got this.
Is there like a head?
Imroot. All right. Get root's a function. Get val's a function. Ooh.
Oh. Is that the one I did?
Yeah, that's all. You got it.
Do you want me to? Yeah. Simple. Oh,
Well, that means you found it. Was that you? Ooh.
This is where we would do all the like left and find the most right of the left.
Sure. So maybe it would make more sense to write a remove function based on, well, not based on the node, but let's
We got another function.
another function.
Oh.
Maybe. So if mroot's equal to val, we'll not return true. Well, I guess return true because you're going to remove it. But I think we meant rover right there.
Oh.
And also, that's only going to check if the first one is rover, but it could be something else.
So we need the while loop before.
Right, so we need while rover does not equal null. So here's where we found it. Otherwise, what do we need to do? So if it's not the current value, and rover's not null, of course, that means val is greater than it. All right, Colin, get left and get right, but yeah, gotta set rover equal to. Yeah.
Oh.
Yeah, someone's doing that right now. Ooh, someone went to replace mode. Nice. Hold on a second. We're back to insert. Okay. All right, let's start setting up some test cases, otherwise it'll get a little tricky. Oh, did I put in source? I did, didn't I? No, I didn't. I put it. Okay. I wonder why that's empty. Let's figure out what the problem is. Huh. Okay. Alright, let's try it again. Perfect. Okay. So let's see what we got here. So test one, we want to assert, right, that we can get the val, those two are null, and then we want to also assert that if we call, well, those are with the nodes, so that does not help. So down here we want to try and do ts assert bst.remove. If we can remove 5, that should be true. And then we'll do bst.print just to see that nothing actually happened.
I misspelled remove.
I sure did. Well, I also misspelled it down here. Let's make sure that gives an error. Good. Remove. Okay, and the 5 is still there because after we remove it, oh, we didn't write our contains function. All right, well that's not what we're doing. We're just going to do remove because contains was part of the previous lab, right? Yeah, it was search, so we're not going to do that in this class. But we tried to remove it, and it returned true, which was good, but it didn't actually remove it. Okay. And let me go over here and take a look at what would be probably a simpler one to remove. So the -30 will be simpler because that one's at a leaf. Yeah, that one's at a leaf. Well, no, wait, maybe not. Let's draw this one on the board. All right, we have 5. What's the next number?
14.
14.
2.
2.
-30.
-30.
7.
7.
19.
19.
And -3.
-3. So that would be right here. So -3 is a leaf. All right. Okay. Make sure that still compiles and runs, but the -3 did not go away. All right. So, we found it. Now what do we need to do?
Check that it's a leaf.
Okay. How do we do that?
If you look at the right pointer and the left pointer are both null.
Okay. Yes. Go, go, go. All right. So node's a leaf, we delete it. All right. How does that look to everyone? Let's see what, whoops. Let's see what happens. A 0 got in there. You want to take a guess?
So
You're just setting that position equal to 0 whenever you delete it.
Well, no, it was deleted.
No, 0 went right in.
But think about this. This guy is holding the memory on his right side. He's over here pointing to null, right? And if we just delete this, this guy's pointing to the old location of the node. We haven't updated this pointer. So we need to update this pointer. All right. Now,
Yeah, but something. Okay, one behind.
I'm gonna try and simplify this a little, although this may get very confusing. But if you get an idea of what this is, what should I call this? Because we want to be able to manipulate this pointer. So this would be, do you want to call it the parent edge? We'll call it the parent edge. Let's see if that compiles. Now I'll show you what this is doing. Nope. L value require unary in amp. Oh, I need to put this. Nope, not gonna happen. L value require, oh, because when you're getting the write, it's actually getting you the node, not the branch itself, which is what I was trying to get. Is it gonna do that for me? No. All right, so I just realized the way we set this up is not gonna allow me to create a pointer to the edge. Well, that's somewhat frustrating, but oh well. So we'll have to do it the other way. Okay. So the parent's rover. So the parent will then be pointing to whatever the parent is. So, well, actually we can delete rover first. Oh wait, no, you don't want to delete rover first. Before you delete rover, you want to check if parent and parent was a get left equals rover. Then what are we going to do to parent set left?
As null.
Yeah, there we go. Do it. Alright, now let's do the same thing with the right. Well, I'll copy pasta that for you. Okay, let's see if that does it. Hey, -3 is gone. Okay, we got case 1 done. That's great. Else if so that was case 1 where the node's a leaf. Let me go ahead and hop over. Let's so that was that test case. Let's call it test 2. Where instead of deleting -3, let's delete 30, -30. So this time, what should happen on the board if we're deleting 30?
2 should point to -3.
Yeah, so 2 should jump down to -3. Okay. How do we do that one? So in that case, what's happening at negative 30 right there?
If get left equals null,
Mm-hmm.
but get right does not equal null.
Correct. So we gotta check for that one first. Go, go, go. Rover.
No, that doesn't work. Alright, I thought that worked.
All right. Well, let's copy that one from up there down to here. So if parent and parent dash get left is equal to rover, then what do we need to set the left here to? Not rover, because rover is what we're deleting.
Or rover.
Get val.
No, not get val is the value.
Right.
So if we're deleting this negative 30, we need to replace it with the negative 3, which is right. So we need to replace it with rover dash get right. Oh, oop, sorry. Go ahead, fix it. Okay. And then we're gonna do this, whoops, we're gonna do the same thing here. And then delete the rover afterwards. All right, let's go see if that fixes it. So the first one, the negative 3 is gone. The next one, the negative 30 is gone. Oh, we're looking good so far. Hey, look, I just copied the whole thing over. Well, this one, hopefully, it falls out, not equal to null on the left, but equal to null on the right. Then instead of getting the right, we get the left. And then let's go ahead and make a test case for that. That would be if we deleted the 2.
So it goes.
And the 2 is gone. All right. Now, for the final test case that we're not going to do in class, that would be if you deleted, the 14. And I think our code does nothing in that case. Yeah, it doesn't delete the 14. So that would be the fourth case. And I'm going to let you all think about how you would go about fixing that problem. Give you a hint. When you, obviously on this board, 14 is not very deep. But one thing you can do is if you go on the left and find the greatest on the right, once you find that value, you can just call delete node, because it's going to go and search the whole thing again and do the shifting for you because you've already written that code. So just call yourself here. It's a little recursive, but that's okay. And then you just replace the 14 with that one, you're good to go. If that was too confusing, that's okay. Watch the video maybe a couple times. Doesn't make sense to you, do it your way. Any questions on this part? Yes, we're doing great today. Nothing so far? Awesome. All right.